Hello, my name's Nigel Bowden. I'd like to welcome you to episode 11 of the Wi-Fi for Beginners podcast. This is a series of podcasts discussing the fundamentals of wireless LAN networking. In each episode, we'll be taking a look at a different aspect of Wi-Fi to build your understanding and knowledge of wireless LAN networks. Each episode is accompanied by a set of slides describing the topics covered in that episode, but you don't need to actually review these as you're listening to the podcast. You can review them later to review some of the information we've covered in a little bit more detail. All of the slides and recordings and other supporting material is available at my website, which is wififorbeginners.com, so you can get along there and download all of those for free. I'm going to jump right into the content today. I'm going to dispense with all the usual introductions. This is episode 11. We're actually on module number 4, where we're talking about more advanced RF theory. You need to go back to episode 10 to hear the first part of the module. As I say, this is episode 11, and we're going to dive straight into the second half of module 4, which is more advanced RF topics. So I'm just going to do a very quick review of the topics we covered in the last episode, just to get you back up to speed and refresh your memory before we press on with new content. So we started off by doing a very quick review of the material in module 2. We talked about things like the way that frequency of RF signals is measured in cycles per second using a unit known as hertz. We also talked about the various multipliers for measuring frequency. So we've got 1000 hertz is 1 kilohertz, 1 million hertz is 1 megahertz, and 1000 million is 1 gigahertz. We talked about the different frequency bands. We've got the low frequency, medium frequency, high frequency bands, all the way up to super high frequency bands. We also just reminded ourselves about the way that as the frequency of a signal becomes higher, the distance over which it's propagated tends to reduce, and also the ability of the RF signal to pass through obstructions also reduces as well. And we tend to think of the analogy of as the RF signal rises in frequency, it becomes more and more like light, and it's harder for it to pass through those obstructions. We also talked about a concept called free space loss, which is the way that an RF signal naturally reduces over distance as it moves through space. We also took a look at RF system basics. We talked about the two basic entities in an RF system, a transmitter and a receiver, and we also talked about a station, which is any device which is accessing the RF medium, which can be an AP or a client in the case for a wireless LAN. And we talked about the fact that two stations in an RF system can only be either transmitting or listening on the same frequency. They can't actually transmit and receive at the same time, and they must be both on the same frequency to be able to hear each other when they are transmitting or receiving. And this mode of operation, when only one station can be transmitting and the other receiving at any point in time, is known as half duplex operation, and all stations operating within a wireless LAN operate in this half duplex mode. We also talked briefly about the coverage area of a station. So when a station is transmitting, its signal can be heard by a number of other stations in the coverage area. They can all hear the transmission of that station, but they can't transmit while that station is actually using that particular frequency. We also talked about a very good analogy for this system. We talked about a walkie-talkie press-to-talk system, whereby if we've got a series of walkie-talkies deployed, only one user at any time can press the button and transmit so that all the other stations in that reception area can hear it. And it's very much the same way with wireless LAN systems. We have this half duplex mode of operation where only one station can transmit at any time, and all of the stations must be receiving. If we do actually get two stations which try to use the same frequency, the same channel at the same time, then all receivers in that area will receive both signals, and we'll end up with garbled information that can't be decoded. This is Cochannel Interference, which is a very important concept within wireless LAN systems. We also talked briefly about CSMA-CA, which is Carrier Sense Multiple Access with Collision Avoidance, very similar to the Ethernet system of CSMA-CD, which is Carrier Sense Multiple Access with Collision Detection, and this is a medium access method which is used to determine when stations can actually gain access to the RF medium and transmit their data. It operates very much in the same way as CSMA-CD on Ethernet systems, where stations will actually listen to the medium to see when it's free, and then they can actually jump in and transmit their data. The only difference between the Ethernet system and the wireless LAN system is that we can't actually detect collisions in the same way that Ethernet can, so we have to use a collision avoidance technique in wireless LAN systems. If you remember, each wireless LAN station has only got one radio in it, which can either be transmitting or receiving at any point in time. So when it's actually transmitting, it can't actually listen to see if it's been involved in a collision with another station transmitting at the same time. So we have to use a system of random number countdowns to arbitrate access to the RF medium. Also, in the same way as in old Ethernet hub systems, the RF medium is actually a contended medium. Each station has got to wait for its turn to use the channel, and only one station can talk at any point in time. The net effect of this, of course, is that the medium is shared between all stations which are within a coverage area, so that all stations talking to an access point are actually sharing the bandwidth which is available over the air between themselves. This is a significant difference in terms of medium access that we get with switched Ethernet networks, where each station has got its own dedicated bandwidth which it can access at any time. It's also got full duplex operation, which means it can use the maximum amount of bandwidth available to it, so it can use it at any point in time, use the maximum amount of bandwidth. So the throughput that we achieve from Ethernet connections are significantly higher than we will get with wireless LAN connections, which are using contended medium with half duplex operation. Okay, so it's time to move on to some new information for this particular episode. I'm going to start off by talking about the concept of channels. It's a term we've bandied about quite a bit in this episode and previous episodes, and just wanted to put a little bit more detail around what we mean by a channel. We talked about various radio bands a number of times. You can think about the 2.4 gigahertz band, the 5 gigahertz band, and these are a wide range of frequencies, and we don't need to use all of the frequencies all at the same time. We tend just to need to use a small chunk of those frequencies for our communication at any point in time, and this small chunk of frequencies that we need is known as a channel. So conversely, a radio system doesn't operate on one single frequency. So if we take a particular frequency from the Wi-Fi band, on the 2.4 gigahertz band we've got a frequency of 2.412 gigahertz, which is a fairly precise figure, and if you've not heard it before, probably doesn't mean too much, but 2.412 gigahertz is the center of channel 1 on the 2.4 gigahertz band, and this is the center frequency of that particular channel. But we don't actually use just that frequency. If you think back to some of the conversations we've had previously about modulation, where we actually take a data stream and we vary some components of the frequency in use in response to that data stream. We've previously talked about frequency shift keying, which is where we just shift the frequency in use up very slightly to represent a binary 1 and down very slightly to represent a binary 0. It's this type of technique that we're talking about, and because we're actually shifting between these frequencies, we actually need more than just the center frequency to convey data. The actual modulation that we use in wireless LANs is more complex than this, but for similar sorts of reasons we actually need more than just one frequency. We need a small range of frequencies that we can work within to convey data, and it's this range of frequencies that we call a channel. And if we look at the lower frequency that's in use up to the upper frequency that's in use within that channel, that gives us this channel width that we need to use to be able to convey data over a wireless LAN system. One example of this is on the 2.4 gigahertz band. If we look at channel 1 of the 2.4 gigahertz band, it actually operates between 2.401 to 2.423 gigahertz. So that probably doesn't mean much if you're listening not looking at the slides, but I can assure you those figures actually correspond to a 22 megahertz channel width. So the center frequency there is 2.412 gigahertz, and we've got 11 megahertz either side to give us that 22 megahertz channel width. So the key takeaway here is that a channel is a small chunk of frequencies that we need to be able to convey information. We can't just operate on a single frequency. And another characteristic of a channel is that as the channel width increases, then the amount of bandwidth we've got to use to transfer data over that channel generally increases, and we actually see this in wireless LAN systems. We talked about the 22 megahertz channel example previously, but we generally talk about channel widths of 20 megahertz that we use as a basic unit of channel width measurement in wireless LAN systems. But in a number of more recent 802.11 amendments, it's actually possible to bond a number of these 20 megahertz channels together to form wider channels that give higher throughput. For instance, in 802.11n it was possible to bond together two 20 megahertz channels into a 40 megahertz channel, which provided double the throughput. In 802.11ac, 4 channels can be bonded together into an 80 megahertz channel, and 8 channels can be bonded together to form a 160 megahertz channel, with corresponding bandwidth gains that you would expect as we increase the channel widths significantly. However, I need to bear in mind that there are some fairly significant challenges to using wider and wider channel widths, as we actually have less and less channels available to use without running into problems with Cochannel interference. So let's return to our discussion of Wi-Fi bands. We've talked a number of times about the 2.4 gigahertz band and the 5 gigahertz bands, and these bands have been pretty much universally agreed across the globe. They're available for use in many parts of the world, and it's pretty much the same ranges of frequencies which are generally available within each of these bands. There are, however, a number of restrictions on the particular channels which are available for use within each country, and this is going to vary by regional and national restrictions. The reason for this is that you will find that some channels may already be in use by other services in particular countries, so they're not available for use. For instance, there may be existing licensed services already operating on some of the channels. There may be services such as military communication systems, radar systems, weather systems, so not all channels are available in all parts of the globe and in all countries. A very good example of this is on the 2.4 gigahertz band. Here in the UK we have 13 channels available on the 2.4 gigahertz band. They're numbered from 1 through to 13, so we've got 1, 2, 3, 4, 5, 6, 7 all the way up to 13 available for use for wireless LAN networks. However, in the USA they only have 11 channels available. It's the same frequencies, and it's a subset of the same channels. They have channel 1, 2, 3, 4, 5 all the way up to 11, but they only have 11 channels available. Channels 12 and 13 are just not available for use by wireless LANs in the USA. So it is key to understand what particular channels are available within your particular region. So a little bit more background on the 2.4 gigahertz band. If you're reading about it in wireless LAN textbooks, you often see it referred to as the ISM band in those textbooks. This stands for the Industrial, Scientific and Medical Radio Band, and this is a USA specific reference. These bands aren't known globally as the ISM bands. They tend to be known in North America as these bands, but wireless LAN textbooks tend to refer to them in this way. Also, the 5 gigahertz band similarly is known as the UNII band in wireless LAN textbooks. This stands for the Unlicensed National Information Infrastructure Radio Band, and again this is specific to North America, and in other countries they will be known by different terminology, but they are still using the same range of frequencies by and large for the 5 gigahertz and the 2.4 gigahertz bands. So for instance, this 2.4 gigahertz band generally uses around 11 to 13 channels in most countries around the globe, and they're all numbered sequentially from 1, 2, 3, 4, 5, 6, 7 all the way up to 11 or 13, whatever the top end is for your particular country. The other thing about the 2.4 gigahertz band is that each channel is only separated by 5 megahertz, so the spacing between channel 1 and channel 2 is only 5 megahertz, and then between 2 and 3 is only 5 megahertz. But to actually operate a wireless LAN channel, as we said previously, we need at least 20 megahertz, so we can't actually use adjacent channels. They're too close together. We can't use channels 1 for one wireless LAN connection and channel 2 for another wireless LAN connection. We have to space them well apart so that they don't interfere with each other, and this gives us the concept of overlapping and non-overlapping channels. So you'll quite often hear the convention of only using channels 1, 6 and 11 on the 2.4 gigahertz band, and this is where this comes from. It if we do use channels that are next to each other, channel 1 and 2 or channel 5 and 6, then we get adjacent channel interference, which causes us a lot of problems with errors and interference and causes very poor performance for our wireless LAN system. You may wonder who actually determines which particular bands and frequencies and channels can be used in different parts of the globe, and there are a number of regulatory bodies. Globally, we've got the ITU, which is the International Telecommunications Union, which has got a global overview of all RF spectrum usage around the globe. They break the globe down into 3 regulatory regions. We've got Region 1, which is Europe, Middle East and Africa. We've got Region 2, which is the Americas. And we've got Region 3, which is Asia and Oceania, and there are a number of global treaties between these different regions and different countries to determine the spectrum that's going to be available for use in each of these regions. And then down at the regional level, for each country there is an RF regulatory body which is responsible for locally managing the RF spectrum in that particular country. And we've got organisations such as the FCC in the USA, which most people have heard of. We've got the ARIB in Japan, which is the Association of Radio and Industries Business. We've got the Ministry of Economic Development in New Zealand, and in the UK here we've got Ofcom at the UK level, and European wide we've got an organisation called ETSI, and those are just a few examples. For each country around the world there'll be their own local RF regulatory body which determines which particular frequencies and channels can be used within that country, and it's really important to know the regulations which apply to your country in order to ensure that you can operate the equipment effectively, and to operate it legally you need to understand things like the correct channels that can be used in your country, what the limits are on any particular transmit powers that there may be. In some countries you have very low transmit powers available on some channels, in others they may be used on much higher power settings. For instance, if you've got a wireless LAN outdoors, and there may also be restrictions on which channels can be used indoor and outdoor, and there can also be regulations determining coexistence with other services such as radar systems. We've got the concept of DFS, which is dynamic frequency selection, whereby channels have to be aware of local radar systems and defer to them if they detect any transmissions from those systems. And again, understanding the regulations for your country is particularly important when you're configuring wireless LAN equipment. When you're configuring controllers and wireless access points, it's important to enter the regulatory domain in which your equipment resides, and also the country that it resides, and this is essential to make sure that it's correctly configured. You're not going to be breaking any local laws with respect to the operation of wireless LAN, and also you need to ensure that your APs are correctly configured so that your clients can actually see all of your APs. If your APs are using channels which aren't valid for your particular country, it may well be that clients which know which country they're in will not use the channels that you've set your APs up on. So it's absolutely crucial that you correctly configure your regulatory domain and country information on all equipment. So just taking a little bit of a deeper dive into the 2.4 gigahertz band. If you look on slide 25, if you're following along with the slides, you can actually see a channel plan of the 2.4 gigahertz band. It actually shows each of the channels 1 through to 13, which applies to the UK here, but it's only 1 to 11 in the US, and it varies in other countries. But you can see the center frequencies that are in use, and you can see that each channel that we need to use for wireless LANs, we actually need a frequency channel width of around about 20 megahertz, and so that limits us to channels 1, channel 6 and 11. So a little bit more about 2.4 gigahertz. It has until recently been the most heavily used wireless LAN band. It was the first one to undergo mass adoption due to the low cost of its components in the early days of wireless LANs. It is still heavily used today, particularly by lower cost devices which may still only be able to use the 2.4 gigahertz band. And one emerging trend at the moment is we've got this Internet of Things which is emerging, where we're getting more and more devices which are all connected to each other, and these lower cost, lower power devices tend to use the 2.4 gigahertz band due to the lower cost of components. So 2.4 gigahertz is still getting busier and busier as we get more and more devices introduced. And we also need to bear in mind on the 2.4 GHz band, it's not just wireless LAN devices which are using that particular band, but we'll talk about that a little bit more in a couple of slides time. As I've already said, one of the big challenges with the 2.4 GHz band is the fact that although we have 11 or maybe 13 channels available, the actual channel spacing between each of these channels is only 5 MHz, but we need at least 20 MHz of channel width to be able to convey our wireless LAN RF communication. Due to this restriction, we have to make sure we have 5 channels worth of separation between all of the channels that we use in the 2.4 GHz band. So for this reason, we tend to use just channels 1, channel 6 and channel 11. So we've got 5 channels of separation between channel 1 and 6 and another 5 between channel 6 and 11. So this gives us just 3 usable channels in the 2.4 GHz band. The difficulty with only having 3 usable channels is that if we need to deploy more than 3 APs in any particular area, which is a very common occurrence these days, we're generally going to need many APs to be deployed, and it becomes very difficult with only 3 usable channels available to place those APs so that APs on the same channel can't hear each other, causing co-channel interference. So that's a particularly big challenge in the 2.4 GHz band that we have to contend with when we're designing for that particular band. So just to recap some of the main points about 2.4 GHz band. In most countries around the globe, we tend to have between about 11 and 13 channels available, and they are numbered sequentially: channels 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. Each channel is only 5 MHz in width, which isn't wide enough for the modulation that we need to use for wireless LAN transmissions. We need at least 20 MHz of channel width, and for this reason we can't use adjacent channels. So we can't use channels 1 and 2, can't use channels 3 and 4, 5 and 6. Any 2 channels that are next to each other you are not able to use without causing significant adjacent channel interference, which is going to cause very, very poor performance on your wireless LAN. So we tend to stick by convention to 3 non-overlapping channels, which is channels 1, 6 and 11. And the other thing to bear in mind about the 2.4 GHz band is that it is used by a large number of other services, things such as Bluetooth devices, microwave ovens, some security cameras, you've got baby monitors. There's a whole range of devices which are non-wireless LAN devices which are using the same band, and they can cause significant interference to our wireless LAN, quite often making the 2.4 GHz band a very poor choice in terms of mission critical applications. And so finally for this episode, just going to talk very briefly about channel planning for the 2.4 GHz band. We need to bear this in mind when we're actually deploying wireless access points. If you get the opportunity to have a look at the slides which accompany this episode, have a look at slide number 28, and I've actually tried to show pictorially there how we try to lay out our AP cells. We can only use channels 1, 6 and 11 as we've already talked about, so we need to try and lay out our AP cells so that no 2 access point cells which are adjacent to each other use the same channel, and it's a fairly difficult thing to do when you've only got 3 available channels. But if you can look at slide number 28, you can actually see we've tried to avoid placing cells which are on the same channel directly adjacent to each other, and the purpose of doing this is to try and ensure that APs which are on the same channel can't hear each other, and so they're not actually contending for the same airtime. If you remember back to our discussion about wireless LANs being a contended medium, if we've got 2 APs which can hear each other on the same channel, then they will actually have to share the airtime between themselves, taking it in turns to transmit on the channel. So this sort of negates the purpose of having 2 access points, because only 1 access point at any particular point in time can talk on that particular channel, so we may as well just have 1 access point. So that's a pretty key part of RF design that you need to bear in mind around the 2.4 GHz band. We've got very limited number of channels, so we have to be very careful how we lay out our AP cells, trying to avoid putting access points on the same channel next to each other. So that's pretty much it for this particular episode. Just to recap the topics we've covered in this one very briefly, we talked a little bit about the concept of RF channels. We talked about the fact that within a frequency band we only need a small chunk of frequencies, which we call a channel, to convey the information that we need to transmit between stations through modulation techniques. We also talked about the fact that in wireless LAN networks the basic unit of channel width is 20 megahertz, but we can actually bond a number of these channels together into 40, 80 and 160 megahertz channels, depending on the 802.11 amendment that we're supporting, to give us wider channel widths and corresponding higher channel throughput. We also talked about the 2.4 and 5 gigahertz bands, the fact that they're available across many parts of the world, but there are some regional restrictions depending on where you are in the world on the channels within these bands that you can actually use. We mentioned the fact that the 2.4 GHz band is often known as the ISM band if you're reading wireless LAN textbooks, and the 5 GHz band is often referred to as the UNII band in wireless LAN textbooks. These are North American references, and there will be corresponding bands in your particular country or region. We mentioned that globally the use of RF spectrum is governed by the ITU, the International Telecommunications Union, and that around the globe there are regional and country level RF regulatory bodies such as the FCC, the AIRB and Ofcom in the UK, and these particular regulatory bodies determine the regulations that apply to the use of wireless LAN in your particular country, and it's important to know how you can use your equipment in your particular country. There will be restrictions on things such as channels that can be used, transmit powers, indoor and outdoor use. So it's absolutely key that you understand the regulations which apply to your particular country so that you can correctly configure your wireless LAN equipment. We also then took a little bit of a deeper dive into the 2.4 GHz band. We talked about the fact that we are limited to only using channels 1, 6 and 11 as non-overlapping channels, and because of this we have to be very careful when it comes to actually planning the layout of our wireless LAN network to ensure that we don't actually have APs that are using the same channel right next to each other, causing co-channel interference. So in the next episode we'll be rounding off our discussion of more advanced RF topics. Please remember that you can get along to my website, which is wififorbeginners.com, where you can pick up the slide deck that accompanies this and all of the other episodes in the series. You can also hear all of the audio, and also we've got some quizzes posted online there so you can check your knowledge of various wireless LAN topics that we've covered during this particular podcast. Also would like to invite you to join the mail list. If you go to the website, on the right hand side of each of the pages we've got a sign up widget where you can actually join the mail list, where I'll be distributing information about forthcoming episodes and other offers and other media that we're going to be making available as I expand the podcast and associated material. So thanks very much for joining me. I look forward to joining you again soon on the next episode of the Wi-Fi for Beginners podcast.